Okay, lesson 4 is on Le Chatelier's principle. And what Le Chatelier's principle does is it explains what happens to an equilibrium reaction when changes are made, and that's assuming the reaction was at equilibrium. So, the best way to explain is just to look at examples. So, in this example A here, our reaction shows equilibrium between hydrogen iodine, and it's breaking up and forming hydrogen and iodine gas separately. Once we get to equilibrium, we know that we're going to have some concentration of both the reactant and the products. So once we get to equilibrium, remember that the concentration of the reactant goes down, the concentration of the products go up, and since both products have a 1-to-1 ratio, the concentrations of both of those will be the same. We know that equilibrium is whenever the concentrations no longer change. So this line here represents when equilibrium is reached. So, the first kind of change that we can instill upon an equilibrium system is adding or removing a species, or in other words, changing the concentrations. So let's say in this reaction here, hydrogen is added. So if we increase the amount of hydrogen, that's going to cause an imbalance. Now, all of a sudden, we're going to have more hydrogen at equilibrium than this system is used to having. And by having too much hydrogen, hydrogen, of course, is a product. And think about what happens when you have too much product. If we think of this in terms of Q, too much product means the reaction will go backwards. So by increasing the amount of hydrogen, this reaction is going to try to shift, it's going to try to use up the hydrogen, so it's going to go backwards. We say it shifts left to consume the excess hydrogen. Because increasing the hydrogen was adding too much product, more product than there should be at equilibrium. So the only way to get rid of that extra product that was added was to use up that product, which means it's going to make more reactant, and that's why it's shifting left. So in the case of removing hydrogen, now all of a sudden we've got too little hydrogen. And so anytime something is removed, the system is going to try to replace it. So if it replaces it, it's going to shifts to the right to replace the hydrogen. Right? So that one's kind of easier to remember. Anytime something is removed or the concentration is lowered, the equilibrium system is going to respond in a way which replaces what was removed. Okay. Now this same idea can apply if we talked about iodine or if we talked about hydrogen iodide. It doesn't matter which reactant or product we're talking about, as long as it's an allowable state, meaning in an aqueous or gas state. Solids and liquids, changing the amount of those does not shift anything. So that's something to remember from an earlier lesson, that we don't pay attention to solids or liquids in equilibrium, the condensed states, only gases and only equilibrium. All right, let's look at example B. So another thing that you can do to cause an equilibrium to shift is to change the volume or change the pressure. So let's talk about volume first. If we change the volume, let's say we increase the volume. So in this first reaction here, what you have to do is you have to pay attention to the number of moles of gas reactants and moles of gas products. So here, in our first example, we've got 1 mole of gas reactants, and on the product side, we have 2 moles. So, if we increase the volume, meaning we give it more space. If we give it more space, then the system's going to respond in a way to maintain a certain level of concentration. Well, if the volume is getting bigger, the concentration is going to go down unless you put more moles in the numerator. So because the products have a coefficient of 2, you're going to have more moles of particles if this reaction shifts to the right. So this reaction shifts to the right to maintain the concentration of particles. Now, by the same token, if the volume decreased, right? If this volume decreased, now we're squeezing it. Squeezing the reaction. If you squeeze the reaction, you're going to have less space. And if you have less space, the concentration is going to go up. So to maintain the same level of concentration as before, the reaction is going to favor the side which makes fewer moles of particles. So because we have 1 mole on the reactant side, it's going to shift to the left to try to decrease the concentration. To decrease the concentration back to original levels. All right, let's look at the second reaction. So here we have nitrogen reacting with hydrogen. So note right away that we have 4 moles. 4 moles of gas on the reactant side. And that's going to end up forming ammonia, 2 moles. So, if we increase the volume, here, then we're giving it too much space. We need to maintain the same concentration, so therefore we have to make more moles. This reaction is going to shift to the left because it's going to need to make more moles of particles to fill all this new extra space that there is. Conversely, if we squeeze it, then it's going to have to exist in a smaller amount of space, so it's going to need fewer moles of particles. So it's going to shift to the right. Now, in the third case, here we have 2 moles, and we have 2 moles. So if the pressure is changed, or if the volume is changed here, there's going to be no effect because there's no advantage. There's no relief from shifting to the left or to the right. So decreasing the volume, it won't change anything. Now, a note about volume and pressure. If you recall back from the gases unit that the volume and the pressure are inversely related. Right? So that means if the volume increases, well, this is the same thing as saying pressure decreases. Right? Think about a balloon. Like the balloon is allowed to get bigger and bigger and bigger. The reason why it's happening is because the forces on the outside are getting less. So their inverse relationship, you can answer questions asking either about pressure or volume if you understand that they're opposites. If the volume decreases, well, that's the same thing as increasing the pressure. Right? So consider, in this case here, if we have a piston system, and if we've decreased the volume, right? So decreased volume, that's going to equal a higher pressure for all the particles of gas in this space. Conversely, if we increase the volume, that's going to decrease the pressure. So how you answer these questions, it's relative to what's happening. So just remember the volume and pressure are opposites. Now, this only affects equilibrium in the gas phase. So if the equilibrium system does not involve gases, then changing volume and changing pressure has no effect. So you have to pay attention to the states in the reaction. Okay, another situation is if temperature changes. So if temperature changes, we need to pay attention to whether the reaction is endothermic or exothermic. And so to review, what we mean by that is that endothermic means heat is required for the reaction. Or in other words, heat is absorbed during the reaction. The opposite of that is exothermic. And exothermic means heat is released. Now, if heat is released, you can kind of think of it as heat being a product. And if heat is a product in an exothermic reaction, that means in an endothermic reaction, heat is a reactant. Because after all, endothermic reactions require heat to take place. So mathematically, when you see a reaction sum or a symbol, the symbol for heat for now, we'll just call it H. If it's endothermic, it's a positive delta H. And if it's exothermic, it's a negative delta H. And this makes sense because think of it as heat is leaving. If heat is leaving, then the change in the heat for the reaction is negative. Whereas if heat is being gained, then it's going to be positive. Okay, so let's look at these examples here. In the first reaction, N2O4 forms 2NO2. Here, the delta H value given is a positive value. It's positive 58.2 kilojoules. So, because it's positive, that tells me this reaction is endothermic, and the simplest way to visualize this is to just write heat as a term on the reactant side. So heat plus N2O4 forms NO2. All right, so since heat is a reactant, if the temperature increases, well, that's kind of like having too much heat, and heat is a reactant. So if this equilibrium system all of a sudden gets too much reactant, it's going to try to use up that reactant, and that's going to cause it to shift to the right and forces it to make more product. If the temperature decreases, well then instead of increasing the heat, you're decreasing it. You're cooling it, you're removing the heat. So any equilibrium system is always going to replace what was removed. So if you cool it down and decrease the temperature, this reaction is going to shift to replace that heat. It's going to shift to the left. So this reaction was endothermic. Let's look at an exothermic reaction. So here, the delta H is negative 92, so the sign negative means that heat is a product. So you can just write heat as a product. Similar logic, if the temperature increases, you have too much product. This reaction is going to try to consume and use up some of that extra product. This reaction will shift to the left. If the temperature decreases, then the system is going to try to replace and to replace it, it's going to shift to the right. So all of these reactions, all of these responses to changes in equilibrium, think of it, it's very much like a teeter-totter. Things need to be replaced, or if you have too much on one side, you got to move it on over to the other side. I mean, that's kind of maybe a way that helps visualize this. Okay. This is part of a unit that we're not going to talk about. A catalyst is a topic of kinetics, which is not in this course. But just so you know, a catalyst is a substance that speeds up reactions. Now, adding a catalyst, if they tell you a catalyst was added, it does not have an effect, it doesn't have a change on the equilibrium position, because it changes both the forward reaction and the reverse reaction equally. So that doesn't leave you with a different outcome. So that's why we say it has no effect. Also, an inert gas. If an inert gas is added to a reaction, so for example, back to, we saw this earlier. Actually, it was HI. In this reaction where hydrogen iodide decomposes and forms iodine. So when the system's at equilibrium, if I add something like helium, which is also a gas, that's not going to have an effect on the system because helium is not a reactant or product. So adding helium doesn't change anything here that's in my reaction, so it's going to have no effect. All right, so if it's not in the reaction, then it's not going to affect it. Okay, so let's take a look at these examples here. Take a minute and see if you can answer them, and then I'll go ahead and go over the answers. Okay, so hopefully you said for the increase in the concentration of iron, increasing the iron will give you too much reactant. The reaction is going to shift to the right, and it's going to try to use up that extra reactant. For increasing temperature, so right here, this is a heat change of positive 50, which means this is endothermic, so heat is a reactant. So if you increase the temperature, you now have too much reactant. It's going to try to consume that extra heat, and it's going to shift to the right. And for the third one, the decreasing pressure, we only have ions here. Both the iron, the thiocyanate, and the FeSCN, 2 positive, these are all aqueous ions. They are not gases. So decreasing pressure will have no effect. So, how do the following affect the equilibrium constant value? If I increase the concentration of iron, while we did answer that that's going to shift the reaction to the right, it does not change the constant. This wouldn't be a very good constant if it kept changing. In fact, the only thing that will change the equilibrium constant value is a change in temperature. So, I should put a little asterisk here. Only temperature change changes KEQ. All right, so let's say we did increase the temperature. Well, when we increased the temperature, we saw that this reaction shifted to the right. So if it shifts to the right, then I'm going to have more product made, and my concentrations of reactants will go down a little bit, which means I have a larger numerator and a smaller denominator. This is going to increase the KEQ because this is an endothermic reaction, because heat is a reactant, and by causing this reaction to shift to the right by changing temperature, this is the result. So remember, only temperature changes can change the value of the equilibrium constant, and you'll need to figure out how the value of the equilibrium constant is changed, right? What did it do to the numerator? What did it do to the denominator? All right. So, demonstration that we would have done is with nitrogen oxide tubes. The reaction for nitrogen oxide is given here. We start off with a tube that contains two gases in equilibrium. They are N2O4, which is a clear, invisible gas, and we have NO2, which is a brown gas. So, if you look here, this middle tube, well, this is a mixture that has both. It's both gases, and it's at equilibrium. So what this is showing you is that in the beaker on the right, this is ice water. This is an ice bath. And the beaker on the left, this is hot water. So it's being heated and it's being cooled. And so if you notice, the one in the ice bath, we have a lighter color. Lighter color than the one in the middle. The one in the middle is room temperature. And the one on the left, the hotter one, we've got a darker color. So take a minute and try to figure out if this reaction is endothermic or exothermic. So the easiest way to think about this is if we look at the ice bath, when you put something in ice, what are you really doing? You are removing heat. And so that you know that the system will shift towards the side that needs to be replaced. So by cooling this, by removing heat, the system shifts to the side to replace the heat, and we see the color evidence shows it's getting lighter. So that means this reaction is shifting to the side that is clear. So this reaction shifts to the left when cooled. And when you're cooling, you're removing heat. So it's replacing heat, which means this reaction is endothermic. Now we could also explain that by looking at just the hot water. By adding heat, the tube gets darker, so the system is making more of the dark chemical product. So by adding heat, by putting in hot water, it shifts the reaction to the right to consume all that extra heat that's being added. And the evidence is that we see more brown NO2 being made. So you can explain it either way, from the perspective of the NO2 or the perspective of the N2O4. All right, so that is Le Chatelier's principle. There are a couple of homeworks to help you practice with this.